All right, we are finally ready to move on to chapter 16. So this is going to all be about integrals. And so we're going to start really basic with double integrals over rectangular regions, just to kind of get our bearings and figure out what it is that we're doing here with our double integrals. And so we're going to look at volumes of solids and iterated integrals. So, as usual, we want to go back and think about what it was that we did in 2 dimensions when we were dealing with integrals, because that's going to inform us about what we're going to do with our 3 dimensional integrals. So, for example, when we had some sort of function f in 2 dimensions, we, would look at it from a to b, and we would take that region and we would slice it up into little rectangles and add all of those up. And this was a way that we could approximate the area under this curve from A to B in between the curve and the x-axis. Sorry, I was writing and drawing there, so I lost my train of thought for 2 seconds. And so we would find the limit as delta x went to 0. So delta x, remember, that was the width of our little rectangles, and we would make those smaller and smaller, but we would add those up and we would get the height of each of our rectangles times the width of the base, and that would give us the area. And then this would give us, if we take the limit as we go to 0, that would get closer and closer to the actual area, and this led us to our integral notation, the integral from a to b of f of x dx. A little bit of notation with this. So remember, a and b, those were our limits of integration. And f of x, we call that the integrand. Dx is our differential. It tells us a couple of things. It tells us the variable, what variables are independent variable. We're finding the integral with respect to x. It's also essentially our width of our rectangles. And so this was sort of our main interpretation of what the integral is that it was the area under a curve. But, don't forget that we had some other interpretations of the integral, that if we took the integral of our velocity function over a time period, this would give us our displacement of an object that was moving. If we had the integral from a to b of a density function, this gave us the mass of that object. So it's not always, area under a curve, but that's what it is a lot of the time. So it's okay for us to, think about it that way. All right, so what's this going to mean in terms of looking at this in 3 dimensions? Well, it's going to be kind of probably what you were thinking looking at that. So, say for example, we have a surface here out in space, and then we take a part of that. We're going to look at a region in the XY plane. So we're going to look at it from A to B on the x-axis and C to D on the y-axis, and that's going to create, at least in this section, a rectangle that's sitting down there in the XY plane. And we can take that region and we can cut it into little squares here. And then we could take each of those little squares and find the volume of those rectangle, or the volume of those solids. So we could find the volume of each of those rectangular solids. There we go. That's the word I'm looking for. And so, this picture that we have here here's a specific example of a surface. And, if we only use, say, 4 solids to approximate the volume under this curve, so again, it's under our curve or under our surface and above the XY plane, we're not going to get the best approximation of that volume. You can see there's a lot of sort of space in here that we're missing. So of course what we want to do is what we would do with those little rectangles that we would do in R2 is that we want to, make smaller and smaller solids. We want to cut up our region into smaller and smaller squares so that as we make those solids smaller and smaller, we're going to get a better approximation to what that actual volume is. So this is an example I saw out of a different textbook, um, where it looked at, making those solids smaller and smaller, and we were getting a better approximation to the volume the smaller that we got. And that just should make sense because you can kind of even see it here, the top of this picture here, that as those solids get smaller, we're getting a closer approximation to our overall shape. Let's see, this is a how many arrows can I draw on one slide? So our definition is that we're going to take our function defined on a rectangular region, for at least for right now, in the xy plane, and it's integrable, meaning just that the integral exists, if we take the limit as delta x goes to 0, um, and that might be delta a. Yeah, it's got to be delta a. Sorry, thinking about my notes here as I'm writing them. So it's that change in that area. So that area that we're talking about is this area here. It's the area of our base. We're going to make that area smaller and smaller, which is going to make our overall solid smaller. So it's the area of that base going to 0, and our volume is going to be the height of each of those solids, which is, what we're finding right here. It's the height of that solid times the area of the base, because the volume is the length times the width times the height. The length and the width is the area of our base. And then the height is the output. It's that z value for some point that is in our little square. And, just like with Riemann sums, you could take that point in your square, you could take it to be at the center there, you could take it at one of the corners, you could take it along one of the edges, but the smaller and smaller that you make those, it sort of makes less difference about where you take um, that point to be in your rectangle or your little square on the bottom there. So again, this is our height, and then this is the area of the base. So we're getting a volume. And if this limit exists for all partitions of R, so any way that we could chop this up, and for all choices of x sub k and y sub k. So again, this is picking, any point in your little rectangle that you make or your little square that you make, um, when in your chopped up squares. Boy, whew, speaking after lunch, it's just as difficult as speaking in the morning, I'm finding. So this is really, again, just saying it doesn't matter how you make those rectangles or squares, at what point you choose to find the height. As long as this limit exists, then your double integral exists. And so we've got our notation here. We've got two integral symbols. So we're going to take the integral twice of our function f of x, y, and then we've got dA. So again, this R, this is our region, and these are going to be our limits of integration. Our function here is still our integrand. This is what we're integrating. And this is our area or our differential. So dA, this is going to be either dx dy or dy dx. And that should make sense because both sides are changing. And so if we go back to this picture here, we've got, this side right here, which is dx, and then the other side over here, which is dy. And both of those could change. We have it divided up into perfect little squares, but those don't necessarily have to be squared. So both of those are changing, and it's essentially kind of independent of each other, but we're trying to make both of those small. And we'll talk about, the order here in a little bit. Okay, so if we want to evaluate an integral, here we have one that's already set up for it. It's the integral from 1 to 4 and the integral from 0 to 2. And we've got our function here is our f of x, y. And then it says dy dx. So the way that we view this is that we've got sort of an integral nested into another integral. So we've got this first one here, sort of everything that's on the inside. So the inside integral symbol and the inside differential. So 0 to 2 and dy. So what that's telling us is actually our limits of integration in the y direction. That we're going to look at this from 0 to 2. And then let's grab a different color. The outer one, so the 1 to 4 and the dx, that's giving us our limits of integration on the x-axis. So 1, 2, 3, 4. And we're going to look at this integral from 1 to 4. So the region that we're looking at is going to be this rectangle right here. There's our region. And the nice thing that's about this is that we can take this sort of inner integral, that 0 to 2, 1 plus 2xy dy. We can take that inside integral first, which we should. We should do that inside integral first. And here, let's grab a different color. X is a constant at this moment. And we're going to integrate with respect to, that's what WRT is. That's with respect to y. So y is going to be our variable. So how this is going to work out is that we're going to integrate 1, which is going to give us y, and then plus 2x. We're going to treat that part as all of that as a constant. So that's all a constant, our 2 and our x. And then we're going to integrate y, which is going to give us 1/2 y squared. So like we're used to, and that should be a 12 and not a 2. Sorry about that. And then we're going to, this is a definite integral, so we're going to plug in 0 and 2. All right, so simplifying things just a little bit just to make it look nice. We've got y plus 6xy squared from 0 to 2. Now remember, these guys over here are y values. Ooh, that's too light for us to read. Let's grab this. Those guys are y values. So when we plug them into our function, we are only plugging them into y. So we get 2 plus 6x. That x is going to just be like a constant, so we're not plugging anything in for x right now. And we're just using the fundamental theorem of calculus. So plugging in 2, plugging in 0, and what do we get? We get 2 plus 24x, because we're going to get 2 squared, which is 4, times our 6, so we get 24. And so this is what we got from that orange integral. So that orange integral we can replace, so we still have the 1 to 4, we can replace that inside orange part with our 2 plus 24x dx. Now this looks like every integral that we ever did in 252. Our variable is just x, single integral. You can do these as set up as that double integral with both the integration symbols, but I kind of like to do it that inner integral first and then taking that answer and plugging into the outer integral. It just helps my brain not get confused. So this one we're going to end up with 2x and 12x squared from 1 to 4. So again, these guys are x values. And now it's just, again, fundamental theorem of calculus. So 4 times 2 plus 12 times 4 squared, and then minus 2 times 1 plus 12 times 1 squared. And I will save us the arithmetic. We get 168. All right, great, fantastic. Well, I have a question. What happens if we swap this around? So we do have to be a little careful because we have to swap everything. We have to swap where our limits of integration are and our differentials. So we've got to make sure that those are the same. So if we swap around the 0 to 2 and the 1 to 4, we also have to swap our integrands. And you know what? I should do this in the same color we did it before. So the inside one, the x one was green. Our outside one was the orange. And then this one is green. So now this is telling us to do kind of the opposite. It's telling us to take our integral with respect to x first. So let's look at what happens. 1 plus 12xy dx. So here, we're going to treat y like it's a constant. So we're going to get x plus, we're going to get 6x squared y from 1 to 4. We're going to plug in 4, and then we're going to plug in 1. Right? And when we combine our like terms and all of that goodness, we are going to get 3 plus 90y. I'll let you simplify that and make sure that I'm correct there, but I'm pretty sure that I am. And now we can take our answer here and plug it in for our green underlined integral. So we're going to now have the integral from 0 to 2 of 3 plus 90y dy. So we're going to get 3y plus 45y squared from 0 to 2. So again, now it's fundamental theorem of calculus. 45 times 2 squared minus 0. And this ends up also being 168, so, or 86, excuse me. So notice we got the exact same thing. It doesn't matter if we had our differential, if we took the integral with respect to x first and then y, or y and then x. Excuse me. And what's nice about this, because this is going to be helpful particularly in the next section, that it actually doesn't matter what integral you take first, whether you do your integral with respect to x first, or y second, or y first and x second. It really doesn't matter. It's going to work the same either way. So that's something nice about these double integrals. And sometimes there's going to be, a time where it's easier to take the integral first, either with respect or with respect to x or with respect to y, which is something we'll talk about as we move along further in this, and particularly when we talk about this in class. So when we are given a question like this, where we want to evaluate the following double integral over a region that we have, and they give us the region kind of defined this way in this set builder notation, and then we've got our integral, we can set this up to do this with respect to x first or with respect to y first. It really, really doesn't matter. And, the main thing that matters is that we've got our region set up correctly or thought about correctly, and that we keep the limits of integration for y with y and the limits of integration for x with x. So this one, we're going to be looking at it from -3 to 3 and 0 to 1. So it's going to be this rectangular region in the xy plane. So there's our region. And I think because I don't want to deal with the rational part of it yet, I'm going to do x second and I'm going to do y first. And I'll show you why here in a second. So it's going to be dy and then dx. So again, remember I need to do y first because these limits of integration that are on the inside are my limits of y. So again, I'm going to look at this inside integral first. So we're going to look at the integral from -3 to 3 of xy squared, x squared plus 1, and then dy. Now, because we're changing with respect to y here, everything that's got an x, that's like a constant. So we could pull any of that stuff that's got x's out in front. So it's like we have 5 times x squared, and when we have that in an integral, we can move that 5 out front. So same thing here. We can take all of that stuff, that x over x squared plus 1, we can move that all out in front. And then take our integral with respect to y. So again, this stuff just stays out in front here. And then we get 1/3 y cubed from -3 to 3. And once again, we use the fundamental theorem of calculus. You're going to get a little tired of using that, because a lot of these are definite. We will see some indefinite ones too. All right, so this ends up being equal to 18, because you end up with 9 plus 9, so times 18. So again, now putting this back in to our integral for what we've underlined in green, we're going to end up with the integral from 0 to 1 of 18x over x squared plus 1. dx. And again, this is an integral that we took time and time again back in 252. And this one we need to do with substitution. So du is equal to 2x dx. This is one of the few times we actually have a 2x sitting there. That's 9 times 2x. So we don't have to move that 2 over, which is a little unusual. I usually tend to do these with a little bit of bad math. I tend not to change my limits of integration, but if that's to be a little bit better, I usually put x equals each of those. You can change your limits of integration if you want, but we're going to get 1 over u du. And I move that 9 out in front. You can or you don't have to. Again, that's up to you whether you move that 9 out in front. But we're going to get 9 times the natural log of the absolute value of u from x equals 0 to x equals 1. So 9 times the natural log of the absolute value of x squared plus 1. So since that's always positive, we don't actually need those absolute value bars. But we can go ahead and do our fundamental theorem of calculus, and we get 9 times the natural log of 2 minus 9 times the natural log of 1. Natural log of 1 is 0, and so we end up with 9 times the natural log of 2. So of course we will do more examples of these in class and some more examples of double integrals in the next video.